You know, I should really, like, schedule streams instead of just doing them randomly. That would be a smart thing to do. Anyways, let's get right back to it. So to kind of recap what we got done last stream and what we're getting done on this stream as well, since this stream is a continuation of what we were doing last stream, is we got some extra operators working. Because before that stream we only had addition working, then by the end of it we had everything up to multiplication and division, and even like the modulus operator. Now off stream I did get the grammar side of all the other operators working, so we should be good to just jump in and get right to implementing them in the intermediate representation and the back end. Let me show you the parser. I changed up the way that the grammar actually worked, so it is a lot simpler than it was before. Think binary operators right here. Yeah, significantly less lines of code now. I actually do want to show off this git diff because I'm pretty proud of it. Now here in the operators, it looks like this, where before I had a separate parser node for every single one of these. This is the pattern I was using before, and this is even the full pattern. Like every single mul, div, all that stuff was a separate node, just like assignment is still. I'm really happy with that. But now what we get to do is actually use the unary operator context. Let's try saying value is equal to, just add in a unary operator there. So now we have a unary operator in the test grammar. There it is. Big to-do statement. Hey, I haven't really been paying attention to this project since your video about it 3 months ago. How's it coming along now? We're making slow and steady progress. A couple days ago, we got the scripting language working. This is its current state, and we're just working on fully implementing every single one of the math operators. And then I'm going to either move on to implementing function calls, or I might rework how I'm currently passing variables into functions, because right now, behind the scenes, this is a structure and we pass a pointer to the structure. And I'm not sure I want to enforce passing arguments on the stack always, because that just adds a little bit of overhead to every single function call. The scripting language is written in Rust. I haven't rewritten the actual engine yet. That rewrite is later, after we get the scripting language working. Specifically because the engine will be using the scheduling system that we write for the scripting language. So it's kind of like one after the other. Huge rewrite of all the engine systems. Might as well write it in another language too, because we're already having to rewrite the core scheduling system for everything. And that basically requires auditing every single file, so might as well write it in another language too. I wish I had spent more time in Go, because people really like it, the way that it handles concurrency. And with the entire point of Brane script being to handle concurrency better, I should probably take a look into that. What are you making Brane script in? We're currently writing in Rust, so this language is Rust. Or at least the core runtime of the languages in Rust. So we parse the text representation, which is what we have over here on the right, and then we translate that into an intermediate language, or intermediate representation, which is the thing that's safe to be serialized and sent over the network. Ideally, the whole point of that representation is you can't represent malicious memory accesses in it, since it doesn't have a concept of real pointers. Though I am considering adding a pointer type, since that would make certain things easier, but then we JIT compile that into native functions, so those can run as fast as native code, theoretically, if we optimize it well enough. The best advice I can give for lower level languages is just have a project you want to build and jump right in. If you want to build a project enough, you'll figure out how it works. Or if you want something like slightly newer and flashier than C, you could start out with Zig, which is like a modern C, so they have a little bit of convenience there. Defer keywords are really, really nice. Yeah, indeed, this is Windows PowerShell. Alright, we've reloaded the context into my brain. And now this is going to complain about all the different operator types. Nuke everything, because it wasn't imported. Now it's imported, and now it works. I'm gonna ignore ref and deref for the moment. Go straight to negate, which is the one that we're actually testing. I do need to write more actual test cases so we can test that everything compiles. But that's a lot of work, and I don't want to deal with that right now. Let's do writer, and then negate. And we'll implement negate here in a second. And real quickly, let us consult the WASM opcode table that we're stealing so liberally from. Alright, let's see. Do they have multiple negates per value type? They do. Let's do it for int and float types. First, we need to actually implement the negate method. I want to put it after the math. The current set of binary operators. After we negate a value, this will return a result. Are you considering writing out documentation eventually? Not considering, it's a certainty. I want people to use this, and people won't be able to use it if I don't document it. So it is an absolute necessity. Fail can't negate structs. Let's move that around. Wouldn't it be better to split your code into different files? I do have it split into different files. I like having entire systems in single files, so an entire compiler, or at least one section of the compiler in one file, or single sections. It just makes it easier. This is only 1,000 lines long. I've written like hand interaction scripts that are 2,000 lines long, so this is nothing. Unless you're talking about like header and source files, like H and CPP files, like C++ has. And in that case, no, Rust doesn't have that concept. That is a outdated paradigm that only C-style languages use, or old languages. And let's organize these by signedness. So all of our unsigned types are gonna fall straight into an error, which is gate unsigned type, because unsigned types are only positive, so you can't negate a value that is only positive. I am strongly considering making pointer a type, because when I eventually write an optimization backend using LLVM, I will need to be able to tell the difference between pointers and ints. Because right now I'm just using ints. Where are we going to put this? Let's put all of them right here for all the binary operators. Why do I do unsigned? No, we want float negation and integer negation. There's not a load effective address. I do need to add like bit operators in here as well. We essentially need to add most of this table, except there are a lot of duplicates you can see here, which we're unduplicating a lot of them. For remainder, we have integer remainder, float remainder. There's signed and unsigned, and then we do float. Then again, there isn't, I might remove the float remainder function, because apparently that's not supported on every device. So if it causes problems when building the quest, may remove it. We need all of the binary operators. That's what we're looking for. I also at some point need to put casting in, the ability to cast between values. There's a bit not, or a bit invert. Oh, these are SIMD operations. That's weird. Oh yeah, that's right. I figured out that bitwise not could be represented as an XOR. That's the one thing I figured out. We have reference, dereference, negate, a logic not, and a bitwise not. I guess I don't currently have a representation for booleans at all. Do I need to add a boolean type? Because the problem is the LLVM represents booleans as a 1 byte value. And if I were to store it anywhere, that would instantly become a full byte value, up to 8. I guess comparisons still work. I would just have to bit cast it upward, or sign extend it up. Bit not is super easy. That's just needs a constant value. Let's not worry about it for now. You know, I should have the automatic dereferencing as part of the document context, if possible, or move that to a separate validation stage, because I don't necessarily want to do full code gen as part of an LSP script. Actually, it's already in. Wait. Means I guess we can move on to implementing this on the back end. So here we'll build int negation, and we can just copy this over for float. Change that to float negation was not a float value. Just like that, we should have a float negation working. Once we get the compiler to actually work, Brane, see what this looks like. So it should act as if it was 5 minus 3. which is 2. Then we need to get the 2, remainder 6, which is still 2. And then if we look at the actual intermediate representation, in here there should be a negation, which there is. And there we go, that is working. What to implement next? I guess the lowest hanging fruit? The lowest hanging fruit for this is a bitwise XOR. Or not a bitwise XOR. I guess we just implement XOR and then we can let the bit inverse or bit negation to do its own thing. So let's do XOR, bitwise XOR. Let's check if there's a float XOR type real fast. So it doesn't look like there are bit operations for float types. Here's build XOR. Actually, that isn't specifying a type. Oh, but it does specify that it needs to be an int value, which means that yes, this does have to be done through ints. That actually makes everything super easy because there's no signedness. We don't have to worry about any of that. No bit operations for float types. Even though technically, like, there's some optimization. Well, actually, that only works with the int representation of values, but you can divide by 2 by bit shifting. I do want a more robust version of this because I can see potentially adding in vector float types, and it's a lot smaller. So let's implement a couple other bitwise operators. Let's do and. Let's do OR. So now we have and, OR, and XOR potentially fully implemented on the compiler. Since I don't have booleans implemented at all, I might just bite the bullet and implement a boolean type. Yeah, the annoying thing is that like LLVM represents bools as 1-bit integers. I would represent them as unsigned 8-bit integers, and I'm not sure if all of the LLVM condition commands would work with that very well. And like for other JIT runtimes too, because I've been consulting CraneLift's API as well when making these decisions. Like, I don't know how it handles conditionals either. How does it handle conditionals? It was built for WASM, so it's probably more open to using full-on integers as booleans. It's like we do if performs a conditional branching if the i32c is non-zero. Yeah, that's how conditionals work in here. And if I do, I guess they wouldn't have a logical and, would they? They would just use bitwise stuff for everything. Like, bitwise stuff should work for the most part. I could just completely ignore regular stuff. So I may do a meme. Okay, let's see the meme. No booleans. Okay, good. You did put it in the Discord meme chat. Good. I am 4 parallel universes ahead of you. Indeed you are. Alright, let's see how fast I can implement these, because what is working during the morning or early afternoon? That is sleeping time. Right. We are working. I am slightly dreading doing conditionals to the point where like we're going to do function calls probably before doing conditional compilation. And if we do logic and or, those are branching because you, like, if you have an AND operator and the left argument of the AND operator is false, you need both of them to be true. So you already know that the result is going to be false if one of them is false. So you don't even evaluate the expression on the right side. But that's a branching operation. I don't want to have to figure out control flow for my intermediate representation yet. I can put that off a couple days. So let's, what was I doing yet? Right, do writer XOR L type left value right. These don't need to be references. We're done with XOR. Let's do OR, and finally and there we go. So I want to implement bit shifts today as well and just get that out of the way. I think it's as easy as the other things, so I'm gonna say yes. Do I even have operands for this yet? No. Do left and then right. Oh, is there signed and unsigned versions of this? I guess, yeah, the final bit of a signed integer is whether it's signed or unsigned because of mathematics. So if you bit shift that would potentially change the sign of the variable to negative or positive. So I guess if you're doing bit shifting as an optimization for dividing by 2, for instance, because I know you can shift right I think, to divide by 2, because binary is powers of 2. So if you shift right, it divides by 2. And shift right, unsigned shift right. That just feels wrong though. Now we do bit shift right, since we just implemented left. Am I gonna get sidetracked and do this real fast? I think yes. Okay, in the interest of getting this done in a reasonable amount of time, I'm going to ignore bitwise not and move on to instead bit shift. Okay, I think that's all of our bitwise operators, base bitwise operators implemented. Those are logic ORs, which means we only have Boolean logic left to deal with, and comparison. Now this is working. Let's see if it builds. We actually need to implement it. There's our shift operation, and I need, for reference, one that does an int cast, and we do build left shift. And we're done? Wait a second, there should be a sign extension. So I was right. That is just a WASM peculiarity. I don't want to have to deal with signed shifts if they aren't part of the thing automatically. But it's weird, I feel like I did have to do signed versus unsigned in, wait, left shift, it doesn't do signing. Shift right might ask us if we want to do sign extension or not. Build right shift, yeah, there's a boolean here. This is why I remembered there being a bool. And this is the signed one. So yeah, right shift has a signed and unsigned, or wait, is only shift right have a signed and unsigned? So shift right, signed, unsigned. Shift left, yeah, only shift right has a signed and unsigned version. So there's shift left, and then there's I shift right and you shift right. So it is crazier than I thought. And I wasn't totally right, and I wasn't totally wrong. Build right shift, but false, no sign extension. And let's go to where these are implemented, and we delete unsigned shift, and we can just rename that shift left. And now we need to go back to the compiler. Why does shift left have shift? Oh wait, duplicate definition. Okay, I forgot to rename it, but everything else looked correct. Make this just shift left, and there we go. That is now properly implemented. Okay, so it's running, building and running. And let's bit shift value to the left by add 2 for 28. So 2, which would be going over from the left, it would be a 0 and then a 1. So then that 1 would get moved over 6. So it'd be 1 and then 7 zeros, which would be 128. Max value of a signed bit integer, which is correct, I think. At least the value moved the correct direction. So I'm gonna determine this as working. Oh yeah, we can have some fun still. Let's do XOR between 6 and 2. Let's see, 1, 2, 3, 4, 5, 6. Okay, yeah, they do have bytes that overlap. And yes, I did just count binary on my fingers. That is something you can do. It makes it so you can count to 32 on one hand. Ooh, we got a panic. Ah, I didn't actually implement them. It's a good thing I checked. Yeah, I'm just going to completely copy that. All right. So now running this should work. 4 and 6. Oh, wait. The and between 4 and 6 is 4, because 6 is made up of the bytes that represent 4 and 2, because this powers of 2. So we are left with 4. I would be left with 4 and not 2. Oh wait, was it XOR? If it was XOR, then 4, yes, it was XOR. So 6's bytes of 2 and 4 would be canceled out by the byte of 2. This is correct. Let's try doing a bitwise OR. So bitwise OR should be 6, is in fact 6. And then let's do bitwise and should be 2, I think? It ended up being 6. Oh wait. Did I remember to switch the operation to an and? No, I did say build and. Let's do the reasoning here. If we have a 2 and a 6, but it's a bitwise and. Bitwise and, right? Is this a bit and? Let's check the, maybe I'm not outputting an and. Maybe this is a compiler issue, not a JIT issue. Bitwise or where is and? There's and is never called. There we go. Now we should actually output an and intermediate representation thing. Then the output is correct because we told it to do the right thing. Did it do correct? It did do correct. Yippee! Alright, I'm pretty happy with that. I think that's where I'm going to leave the stream today, because I have other stuff I need to get to, because I took too long to actually start streaming, so I don't have a lot of time. This is why I was like, oh, I should schedule my streams. Any lunatics that also want to mess around with it, yeah, it's there. Implement bit operators. Bitwise operator. B, we have bitwise operators, but not booleans. Technically, you can do bitwise operations. You can do boolean type things with bitwise operators, which is probably what I'm going to be doing behind the scenes. Alright, that is it for today. For those of you who stuck around, thank you. I will see you next stream.